Now, having talked about assets and bases, and I hope we can now define an asset. What's an asset? A substance that produces hydrogen ions as the only positive, dissolves in order to produce hydrogen ions as the only positive ions. What is a base substance? Okay, a soluble base for that matter is a substance that dissolves in water to produce hydroxide ions as the only negative ions. Now, we have also talked about a strong acid and a strong base. What is a strong acid? It's one that undergoes complete ionization. Whereas a strong base is one that undergoes complete ionization also to produce OH. So what is produced that differs? What's a weak base? Is one that undergoes partial ionization. Please forget the ideal of one that has a pH 10 or one that has very many hydrogen ions. Please forget that. Just stick to partial and complete ionization, on which you can refer to dissociation. Having talked about that, let's get to amphoteric oxide and hydroxide. Now, we've said that we know that metal oxide and hydroxide are bases, right? That's what we said in Form 1. Therefore, metal oxide will react with that unless they are forming an insoluble salt. This is no news. This is what we call a neutralization reaction. When an acid reacts with a base to form a salt and water only. So we expect this to happen with all metals unless they all metal oxide and hydroxide unless they form an insoluble salt. But then we have an interesting scenario here. What happens when you react? When you add sodium hydroxide to solution that contains some cations. Now, because that is going to lead us to a very interesting phenomenon. What will happen is, let's see. Now, when you have a solution that contains some metal ions, that is metal ions M, let me represent ions like that. Then you add sodium hydroxide. What I am expecting to happen is that I'm going to get a metal hydroxide, which is definitely a base. It is definitely basic. Now, I want to find out whether this base, apart from the fact that it's obviously going to react with an acid, can this base react with sodium hydroxide? Can it react with, because if it does, then it has both acidic and basic properties. That is what this experiment will be all about. We want to see, and this is something that you should be very keen about. It is a basis of what we call the qualitative analysis that is used to test for cations, especially to test for cations. So I want you to follow through and see what do you get. For if I have calcium ions, then I add sodium hydroxide. Obviously, I may get a white precipitate. What about if I add more of the sodium hydroxide? Will the precipitate react with sodium hydroxide? Because if it does, it will dissolve. So let's look at all the ions and discover what happens. Then, of course, for the sake of comparison, I will also use the ammonia solution. What happens when you add ammonia solution to the solution that contains some given ions? So let's observe that clip, and then we shall. Okay, this is a theory of that the experiment that you just done. Now, when you add sodium hydroxide to a solid that contains some metal ions, as I said previously, this precipitation reaction will take place. There will be a double decomposition. So we are talking about a substance AB, that is positive, that's negative. Then you are adding sodium hydroxide. This will happen, double displacement. So there will be an AOH and a sodium salt of B. Now you realize that all sodium salts are soluble. They are all soluble. So if there is an NAB, if that is formed, then you will not see anything because it is obviously aqueous. But then the OH can either be solid or all aqueous. If it is aqueous, then there will be no white precipitate. So when you add sodium hydroxide to a solid that contains some cations, there are two things that you can have that can be seen. You may get a precipitate or you may not get any white precipitate. Now, note that I said you may get a precipitate or no white precipitate, because if the saline is colorless, then you add sodium hydroxide, what are you expecting? I'm expecting a white precipitate. So I don't see a white precipitate. So it would be wrong to say saline remains colorless, no observable change, no white, no precipitate. All those are wrong. So the correct way of putting it is that there is no white precipitate, because the observation should be given with respect to what is expected. So it is colorless. What are you expecting? A white precipitate when you add sodium hydroxide. So what have you seen? No white precipitate. So when you see no white precipitate, what does that mean? That MOH is aqueous. Aqueous. So what must M be? M must be, so the resultant substance is what you call an alkali. The MOH is an alkali. And alkalis are only those of sodium, potassium, and ammonium. So M is either potassium, sodium, or ammonium. So that you get potassium hydroxide, which is aqueous. You get sodium hydroxide, which is aqueous, or ammonium hydroxide, which is aqueous. The other thing that you may see is a precipitate. You may see a precipitate. So if any other thing, it will be if it is not no white precipitate, it's obviously a precipitate. But precipitate may be white or color. Now the colors are few. We have a green precipitate in the case of iron 2, because iron 2 hydroxide is green. The iron 2 salts are green. But you need to be very careful about a green color. Green color, copper 2 salt are sometimes green. Like the copper 2 chloride, the copper 2 nitrate, the copper 2 carbon is green. But in this case, we are talking about the hydroxide. So you get a dark green, or what some people describe as dirty green. I'm not very much concerned about your descriptive term. I'm just interested in the green color. So the dirty is just descriptive. So it's a green precipitate of iron 2 hydroxide, because the iron 2 hydroxide is insoluble. It can be a brown precipitate if you have iron 3. Iron 3 forms a brown precipitate, whereas copper 2 will form a blue precipitate. So the precipitate can be either white or colored. If it's colored, then you don't need to do any further test. No more, you don't need to do a further test. What about if the precipitate is white? Here we have a myriad, we have many of those. The rest of the world will form a white precipitate. So I will not want to make a commitment on what may be there. But I want to add now excess sodium hydroxide, because that will help me to reduce the number of ions that may be there. Now, if the saline contains some zinc ions, then you add sodium hydroxide. What does it form? it forms zinc hydroxide. But zinc hydroxide reacts with sodium hydroxide. Why does it do that? Because zinc hydroxide has both acidic and basic character. It reacts with acids. It reacts with the acid as we discovered at the beginning because they are base. But now it is also reacting with a base. It's reacting with a base. It's both acidic and basic character. Now such an oxide or hydroxide is said to be amphoteric. So the word ampho is derived from the word amphi, which means both. So a substance that has both acidic and basic character is said to be amphoteric, as opposed to a substance that has neither acidic nor basic character. So such will be said to be neutral. So oxides can be said to be acidic. Acidic oxides are normally non-metal oxide, carbon 4 oxide, sulfur 4 oxide, nitrogen 4 oxide. Those are non-metal oxides, they are acidic. Now, oxide can also be neutral. Actually, again, non-metal oxides are also neutral. Nitrogen 1 oxide, carbon 2 oxide, they are neutral oxide. Then, oxide can be basic. Those are metal oxides. Potassium oxide, magnesium oxide, but they can also be amphoteric. Amphoteric are both acidic and basic. So we have three such. That is the oxide of zinc, the oxide of aluminium, and the oxide and hydroxide of lead. I've heard of people talking of ZAP, zinc, aluminium, and lead. ZAP. So zinc 2 hydroxide, aluminium hydroxide, lead 2 hydroxide are all amphoteric. So once the hydroxide is formed, it is also capable of reacting with sodium hydroxide because it has both acidic and basic character. And look at the substance that has been formed. Now it's when you look at that far, so we get, now we could visualize this as a coordinate board. So maybe the zinc has some having lost the outermost electron, it has the 8 electron, the inner energy level, that it will form a coordinate board with the hydroxide. It will form a coordinate board with the hydroxide. Now that it has 4 pairs of electrons, we could say that it's going to coordinate with 4 of the hydroxides. It is going to coordinate with 4. So it forms a coordinate bond with 4 of the hydroxide. So we call this a tetrahydroxy zincate. We write it here zinc OH, and they'll follow that. So zinc has a charge of 2 positive. Each of the hydroxide has a charge of -1. So -1 times 4 is -4. -4 plus 2 is negative. This is a complex that we call tetrahydroxy zinc. Similarly, the same will happen to lead. It will form the tetrahydroxy aluminate with a charge of course, positive 2. Then aluminium will form the tetrahydroxy aluminate with a charge of positive 1. Why positive 1? -1 times 4, -4. -4 plus 3, that is positive 1. So that is a tetrahydroxy aluminate. So then, when you add excess sodium hydroxide to a solution, to a solution that contains some cations, you may see a white precipitate that dissolves in excess. Why does it dissolve in excess? Because the resultant hydroxide is amphoteric, and we have only 3 such: zinc, aluminium, and lead. The rest of them will not dissolve in excess. So we are talking about magnesium and calcium. They don't dissolve in excess. Similarly, so that's what we have been talking about. So zinc reacts with both acid and bases. It has both acidic and basic character. It is said to be amphoteric from the word amphi, which means both acidic and basic character. So other amphoteric oxide and hydroxide are zinc, aluminium, and lead. So these are the reaction that takes place. So if we are talking of the zinc oxide with sodium hydroxide, zinc oxide being amphoteric, react with sodium hydroxide to form the zincate ion. Zincate ion. Note that the coordination number are 2 for the oxide. There are 2, 2, 2, and water molecule is formed in the process. Now you could bring the water molecule here, this side, then you get the tetrahydroxals, the tetrahydroxal zincate, the tetrahydroxal brambate, the tetrahydroxal aluminate. Now, so those are the reactions, but what you need to note is that they are all coordination number 2, and water is formed. So the zinc oxide and hydroxide, the zinc oxide, the oxides are amphoteric. What about if they are in form of the hydroxide? So those are the reactions. The red hydroxide reacts with sodium hydroxide to form the tetrahydroxal brambate, and so on and so forth for all the others. So note how we name the complexes. We start with the coordination number 4, that is tetra. Then what is this? It's a hydroxo. If it was a ammonia, it would be an amine, tetramine. It is water, it is hydro or aqua. So we talk of aquarumin, like the one that is used in the extraction of metals, hexafluoroaluminate, the cryolite. It is hexafluoroaluminate. It's still a complex. So tetrahydroxal. Then this complex will end with 8. Why? Because it has a negative charge. So we talk of nitrate, phosphate, carbonate, because they are negatively charged. Because this complex is negative, as we have just, oh sorry, I messed this up, these negatives. Let's make that correction. These charges are negative, because negative 4 plus 2, that is negative 2. So they are all negative, and that's why they end with 8. That's why they end with 8. Now I want us to note this one thing. If I add an acid to the complexes, what will happen? If I add nitric acid to this complex, why did I get this complex? Because I have excess sodium hydroxide. The acid reacts with excess sodium hydroxide to give us salt and water. So the nitric acid reacts with excess sodium hydroxide to go form sodium nitrate and water. Now, so I no longer have excess sodium hydroxide. Yes, so I revert to the red hydroxide. But red hydroxide is insoluble. So I will precipitate the insoluble hydroxide. In fact, this is a reaction that we shall use in the extraction of aluminium, where we add excess, where we add the ore bauxite to sodium hydroxide. It forms the tetrahydroxal aluminate. That's because the sodium hydroxide is in excess. When we now continue, when you bubble carbon 4 oxide, it reacts to the excess sodium hydroxide. What does it form? Sodium carbonate and water. Then we revert to the aluminium hydroxide, so you can precipitate the hydroxide. So this is what will happen if you have a solution. Now the tetrahydroxal aluminate, if you add an acid, it forms a white precipitate. White precipitate of what? The insoluble hydroxide. When you continue by adding the acid, this hydroxide can now react with the acid to form lead nitrate. So you'll get a white precipitate that dissolves in excess. Just like you got a white precipitate. So when you started with the zinc ions, you added sodium hydroxide. What did you see? A white precipitate of what? The insoluble zinc hydroxide. When you added excess sodium hydroxide, what did you see? The precipitate dissolved. Why did it dissolve? Because of the formation of the tetrahydroxal zincate. Similarly, now I can start from here. The tetrahydroxal zincate with a charge of -2. Add an acid like hydrochloric acid. What will I have? A white precipitate of what? zinc hydroxide, because I no longer have the excess sodium hydroxide. When I continue adding the acid, the hydrochloric acid, the zinc hydroxide now will react with the hydrochloric acid to form the soluble zinc chloride. So the white precipitate that dissolves in excess will be formed either with the cations or from the complex. Now what about with ammonia solution? Now when I dissolve ammonia in water, it will react reversibly. Why does it react reversibly? Correct. I hope what you have said is that ammonia is a weak base. So it ionizes reversible to form the ammonium ion and the hydroxide ion. So what will happen if I add ammonia solution to a solution that contains some cation? So I expect obviously that the insoluble hydroxide will be precipitated. So I'll either get a precipitate or no precipitate. When do I get a precipitate? Let me start from the precipitate. If the resultant because this is what is active now. This is what will react. The hydroxide ion in the ammonium hydroxide will react to form the insoluble hydroxide. So whatever substance form an insoluble hydroxide will form a precipitate. And the precipitate may be either colored or it can either be white. So you will obviously now then when you add excess ammonia solution, again the precipitate may dissolve. But this time it is not due to the hydroxide. So it is nothing to do with the amphoteric character. It is because of the ammonia. And that is important. So it's when you add excess ammonia solution, you will not compress the ZAP. You will not dissolve the hydroxide, the tetrahydroxide. What you'll dissolve is the tetramine. The tetramine. So there are only three substances that complexes with ammonia. That is zinc, copper, and silver. But silver is in another syllabus. We don't say much about it. So when you add a few drops of ammonia solution to a solution that contains zinc ions, what you get? A white precipitate of insoluble zinc hydroxide. Remember the hydroxide ions? So they will form a white precipitate. But when you add excess, the ammonia now, because in that solution we have ammonia, we have ammonium, when we also have the hydroxide. So the ammonia now can complex with zinc to form the tetramine zinc, and this is in form of a salt. So that precipitate will dissolve because of the formation of that complex. Similarly in the case of copper, but the precipitate this time is pale blue, as we said, but it dissolves in excess to form a dark blue solution. Forms a dark, and note, it is dissolving in excess to form a dark blue solution. Not that, now some people will have the tendency to say that when you add, it turns blue, it turns dark blue. What have you told me? That the precipitate is still there, but this time it is dark blue. That is not true. What has happened is that it has dissolved in excess to form a dark blue solution. I hope you see the difference between forming a dark blue, changing to dark blue, or dissolving in excess to form a dark blue solution. So the correct way of putting it is that it dissolves in excess to form a dark blue solution. And that has already been observed in the cream. Now something interesting with the case of calcium ions. The case of calcium ions. You realize that when I add sodium hydroxide to a solution that contains calcium ions, I get a white precipitate. I get a white precipitate that persists in excess. Why? Because I'm getting insoluble calcium hydroxide. But when I add ammonia solution to a solution that contains calcium ions, I get no white precipitate. And why is that so? Why is that so? This is the explanation. Now we have just said that ammonia is a weak base. Ammonia solution is a weak base, meaning what? Which it undergoes partial ionization. So the number of hydroxide ions in that solution is very small. There are very few hydroxide ions because they are weak base. Yet calcium hydroxide is slightly soluble. It's slightly soluble. So when you have very few hydroxide ions, whatever calcium hydroxide you will form will dissolve because it is slightly soluble. But when you have very many of the hydroxide ions, whatever calcium hydroxide you will get will not dissolve because it is too much. It is slightly soluble. So you realize that can be used to distinguish between calcium and magnesium ion. When you add sodium hydroxide, drop point still in excess to a solution, you get a white precipitate that persists in excess. What does that mean? It is not the potassium sodium cast, it is not the ZAP, so it is either magnesium or calcium. Those two, they will form a white precipitate that persists in excess. But so when you now add ammonia solution, calcium will not form a precipitate. Why? Because it is slightly soluble, but magnesium is almost insoluble. So calcium hydroxide is actually more highly soluble. It is very soluble in water. So it will not form a precipitate with ammonia solution. And that is what we have been saying. Calcium is slightly soluble. Ammonia is a weak base, slightly soluble weak base. So calcium forms as a calcium hydroxide that is within the solubility limit with ammonia. But with sodium hydroxide, which is a strong base, it forms calcium hydroxide that is beyond the solubility limit. So it cannot dissolve. It will not dissolve. It will be too much. It will be so much that it cannot dissolve. And therefore that is what we can. So we can use that to distinguish between the two. Now the chart I have here is a summary of what we have been talking about. So your solute contains cations X. You had a few drops of ammonia solute. What do you expect? Either no white precipitate or the precipitate can be formed. So if there is no white precipitate with sodium hydroxide, remember what does that mean? Soluble hydroxide. And what's hydroxide soluble? Potassium, sodium, and ammonia. See the confirmatory test for the ammonium ion. You just warm, and if you get a gas that changes a red litmus paper blue, that is ammonia gas, and therefore ammonium ion could have been in that solute. But you need to be careful about that test because nitrate also produces ammonia, but that's you require to add sodium hydroxide, aluminium, and also in the presence of a nitrate you will get ammonia gas. So you need to be careful about the production of ammonia because it could be testing for the ammonium ion or the nitrate ion. The confirmatory test for the sodium ion is of course the frame test. The same will apply to the potassium ion. Burns in a yellow frame, burns in a lilac frame, and those are the confirmatory tests. So the precipitate can be white or colored. If it's colored, it can be colored blue for green for brown for right. If you can remember that, you are okay. Then you add to the white precipitate, you add excess sodium hydroxide. Two things can happen. The precipitate can dissolve. Why does it dissolve? Because we have amphoterics. Amphoterics, ZAP, zinc, aluminium, and lead. Or the precipitate can persist in the case of calcium and magnesium. Now the other thing with ammonia solution, so you add a few drops of ammonia solution, you can observe either no white precipitate or white precipitate. If no white precipitate, there's the potassium, sodium, ammonium, and then we add calcium. Why? It is slightly soluble. So you add calcium there that you had not added in the previous one. So the precipitate can be either white or colored. Note that for the copper in excess to dissolve, to form a dark blue solution. Now, what about with the white precipitate? Now add excess ammonia. Two things can happen. It can dissolve, it can persist. Only dissolves in zinc, because copper, we cannot bring copper here because it's not white. Only dissolves in zinc. Then it will not dissolve in magnesium, lead, and aluminium. So we can use ammonia solution and sodium hydroxide to test for whatever cations. Although we shall also borrow some other ions. Let me give an example. Now I have a solution that is suspected to contain aluminium ions. It is suspected to contain aluminium ions. How do I go about confirming that it contains aluminium ions? The first thing I'll do, add the sodium hydroxide. What do I see? White precipitate dissolves in excess. But that is not necessarily because of aluminium. It can either be due to zinc, aluminium, or lead. That is using sodium hydroxide. So I add sodium hydroxide to that. I'll have three. It's the zinc, aluminium, and lead. Then I go on to add ammonia solution. I'll see a white precipitate that persists in excess. So with ammonia, I will have eliminated the zinc. So I have the aluminium and lead. So how do I confirm between aluminium and lead? I use the solubility rules that the sulfate and chlorides of lead are insoluble, whereas the sulfate and chloride of aluminium are insoluble. So I can, if I add to another portion, if I add some sodium sulfate, I will definitely see no white precipitate. That confirms the presence of aluminium. And that is the way you are going to be testing. It is going to be a series of elimination. Now, let us therefore get back to that creep. That on the addition, the creep on the addition of. Let us go through the creep again, but this time you can pause the video before the reagent is added and predict what should be observed in a given experiment and probably explain. You can even write an ionic equation, you can write an equation and master that concept because it's very important for your qualitative analysis. This now when you've done that, this becomes my summary of the effect of sodium hydroxide and ammonia solution. And you can still go through it and probably explain each of them. Each of the observation can be explained. So sodium hydroxide is added to magnesium. What happens? I get a white precipitate. Why do I get a white precipitate? Because magnesium hydroxide is insoluble. What about when I add excess? It does not dissolve. Why? Because magnesium hydroxide is not amphoteric, it's not ZAP. Then I get to ammonia solution. I add ammonia solution, a few drops of that. What do I see? A white precipitate. Why? Because of the formation of magnesium hydroxide. Magnesium 2 plus hydroxide ions to form magnesium hydroxide. What about when I add excess? It does not dissolve in excess. Why? Because only copper, silver and zinc will complex with excess ammonia. Then get to the calcium. It forms a white precipitate with sodium hydroxide. Why? Because the calcium hydroxide formed is beyond the solubility limit. So, but what about with ammonia solution? It doesn't form a white precipitate because of the slight solubility of ammonia solution. So once you've done that, you can again go through each of them and be in a position maybe to explain each one of them again. So spend time on this because it is a very important concept. The concept of the qualitative analysis. Furthermore, the trend nowadays is will require that you write a procedure for yourself. So you really need to understand. You need to understand exactly how qualitative the principle behind qualitative analysis. And this is what you will come across in an exam. What we'll refer to as qualitative analysis. But what I've just said is that you may be expected to write your own procedure. But let's look at this one, the way it has been. We've been given the procedure. We've been told that you've been supplied with a solid C7 to carry out the tests and record the observation and the inferences in the spaces provided in the table. Now you press the return of C7 in a dry test, and note that the test tube must be dry. Then you heat gently. You feel that observation. Now when you heat a substance, what are you looking for? Now I expect you to be on lookout for the three states: the solid, liquid, gas, let's say aqueous. Now aqueous in the sense that some solids when heated will first appear to melt, but then they will change back to solid. Actually what has happened to that solid is that it has dissolved in its own water of crystallization. So you could heat a solid, then it just melts. Then you need to make that observation. Now, if you are expecting a gas, now let me start with the liquid. A liquid can form on the cooler part of the apparatus. So when you heat, you have a liquid that forms on the cooler part of that test tube. Note that we say liquid forms on the cooler part, not liquid condenses, because it's already a liquid. How can it condense? Okay, vapor can condense, but a liquid cannot condense. There are some textbook that talks of liquid condensing. So you need to be on lookout for that. That is not allowed. A liquid can form on the cooler part of the test tube. Now, if a liquid does not form on the cooler part of the test tube, then you could hear some crackling sound, as long as the solid was crystalline. So those two observations are mutually exclusive. They are contradictory, or so we say. So you cannot both see a liquid forming on the cooler part and then the solid crackling, because the fact that a liquid is forming on the cooler part of the test tube means that the solid is crystalline. It contains water of crystallization. So if it contains water of crystallization, then it cannot decrepitate. It cannot form the crackling sound. Because where do the crackling sound come from? If the substance is crystalline, yet does not contain water of crystallization, it contains air in the crystals. So when you heat, the air will expand and the crystal will crack. The case of red nitrate, it is crystalline yet does not contain water of crystallization, so it decrepitates. It produces a crackling sound. So if you say it produces a crackling sound, at the same time you say a liquid forms on the cooler part, then you'll miss the two of them, because that is a contradictory observation. So the other thing that you can also see, apart from that liquid forming or the decrepitation, then the gas. A gas may be formed. A gas, and how do you know a gas has been formed? You'll be supplied with either a litmus paper, or you'll be given a sprint. So if you're not given a sprint, don't ask for it. You're not supposed to be testing for any gas that relies on burns in a pop sound. So if you are not given a litmus already, you don't ask. You use whatever that has been supplied. So if you use a litmus paper, you must say something about both of them. Both litmus paper. The blue litmus paper changes red. The red litmus paper remains red. Does not change. That is not allowed. The red litmus paper remains red. So if you say something about one of them, then that is not a correct observation. So in this case, this we are given the conclusion or the inference. C7 contains water of crystallizing, all is hydrated. So what did we say? C, so that you can conclude that obviously a liquid forms on the cooler part of the test tube. Now an acidic gas is produced. What did we see? We must have tested with the litmus paper. The blue litmus paper changes red. The red has remained red. Now the other procedure here, you press in a boiling tube, add 10 cubic centimeters of water and shake well. Now you're not being asked to write an observation there. But what you need to look for is, does the solid dissolve? And what is the color of the solid? So if I had some space for writing conclusion observations here, I would say solid dissolves, forms a colorless solution. Yeah. If it dissolves, then it is soluble. The solid is soluble. If it forms a colorless solution, then colored ions are absent. All I can say, copper ions, ion 2 ions, and ion 3 ions are absent. Yeah? But now I've not been asked to write an observation of that. If it does not dissolve, then you don't commit yourself to insolubility. You state the color of the residue and the color of the filtrate. Yeah? So the solid forms a white residue, colorless filtrate. So slightly soluble, or contains a soluble and an insoluble mixture if you are told it is a mixture. Now to the first portion, add dilute sulfuric acid. Two things. When you add sulfuric acid, there are two things you should be on lookout for. Number one, you should be on lookout for bubbles, because carbonates and sulfides will form bubbles. Bubbles of carbon dioxide, bubbles of sulfur 4 oxide. Now the other thing that you can see with sulfuric acid is a precipitate, because there could be insoluble and insoluble sulfate. That may also apply to hydrochloric acid, bubbles and a precipitate. But if it was nitric acid, then you cannot expect a precipitate. Why? Because all nitrates dissolve. You can see bubbles, but you cannot see a precipitate with nitric acid. What have you seen in this case? So whenever you add sulfuric acid, now there are two folds reaction. A with B can form bubbles. No, H with B can form bubbles. If this is a carbonate or a sulfide, A can form a precipitate. If this is lead or barium or calcium, so it can form a precipitate. So no white precipitate with sulfuric acid. What do we therefore conclude? That if there is no white precipitate, that means that the resultant sulfate is soluble. So that is the absence of lead, barium, and calcium. They are absent. What about no bubbles? No bubbles means we don't have the carbonate or the sulfide. So you write no carbonate, sulfide are absent, and that. So what about now we continue to the second portion, add sodium hydroxide. Sodium hydroxide, drop price still in excess. Now the first thing, we are suspecting aluminium ions and something else, and you must write them in the correct formula. Don't write names. Correct formula. So we are suspecting aluminium ions. So what did we see with sodium hydroxide? Definitely we saw a white precipitate that dissolved in excess. That's why we are suspecting aluminium ion. What else can be suspected? And I think the other thing that we can suspect here is zinc. Zinc can also be suspected, and lead can be suspected. But no, lead cannot be suspected. Why? Because in the previous one, we have said lead is absent. Lead is absent because it would have formed a white precipitate with sulfuric acid. So if you put lead here, it is contradictory. It is penalized. Half a mark will go. Half a mark will go. So I strictly put zinc ion here, and of course the aluminium is given. The observation is white precipitate that dissolves in excess. To the third portion, I add ammonia solution, drop price still in excess. Now aluminium is confirmed. So from here I have eliminated zinc. What did I see? So that I can confirm the presence of aluminium ion, I must have seen a white precipitate that persists in excess, so that I now know it is not the zinc ions, because zinc could have dissolved in excess of that.